I, I see all the people that should be here. So I think we can start. It's a really great pleasure to have Professor Luciano Rezzolla visiting us today. Actually, he will give two seminars, even though he is traveling since 2 in the morning, which I find remarkable. So Luciano Rezzolla is the chair of theoretical physics at the Institute of Theoretical Physics at the Goethe University, Frankfurt, Germany. His main research topics are astrophysical compact objects such as neutron stars and black holes. And he also has written some numerical general relativistic hydrodynamics, a very main book. He is a member of the executive board of the Event Horizon Telescope collaboration that delivered his first pictures of the environment around the black hole at the center of the galaxies. Another book Luciano wrote is for the general public, The Irresistible Attraction of Gravity, which was recently translated into Greek. And actually tomorrow at the International Book Fair, there's another event at 5 o'clock. We have a poster upstairs about the presentation of this book. Luciano Rezzolla has received numerous prizes, including the Karl Schwarzschild Prize, the Frankfurt Physics Prize, the Golden Seal of the University of Bari, the 2020 Breakthrough Prize for Fundamental Physics as a member of the Event Horizon Collaboration, and the Einstein Medal also as a member of this collaboration. And since 2019, he is the Andrews Professor in Astronomy at Trinity College Dublin, and he also has received large grants such as ERC Synergy Grant in 2014 and an ERC Advanced Grant in 2021. So it is a real pleasure that we have you here, Luciano. Thank you very much, and we are looking forward to your work.
Thank you. Thank you, Nick. I know Nick since a long time. I don't want to say how long, but just to give you an idea, dinosaurs were still running around when we were kids. So this wants to be a friendly seminar. I see there are so many young students, and I invite the students to stop me at any time if I say something that is not clear or something that is wrong. And now, today in the morning, I will talk about Newton stars, and I will first tell you about why they are so rich in terms of physics and astrophysics. I will discuss a topic which is called gravitational wave spectroscopy, where Professor Segura has provided very important contributions. I will tell you about two events that we've seen in terms of binary neutron-star mergers and how this has shaped our understanding of what equation state one has and what is the maximum mass for neutron stars. I will go over to using binary neutron-star merger to investigate the possibility of going into a quark-heaven phase transition. And last but not least, again, talking about equations of state. Again, Thessaloniki provided to Professor Thessaloniki's great contributions in this topic. I will tell you about a very simple issue, the issue of the speed of sound in Newton stars. So, as a theorist, I tend to oversimplify in the attempt of getting some basic understanding. And when you think about two compact objects merging, you can think that this is effectively a scattering problem between two bodies. So you start with setting an interaction, okay, a Lagrangian, let's say gravity. Then you have a system for which you assign some initial data, some linear momentum, and then you evolve the system to follow what is the result of this scattering. And you can think that this is what happens in the case of black holes. So you start with two black holes, and as a result of this scattering, you normally, not always, but you normally obtain another black hole plus gravitation. Theoretically, we were able to solve this problem already in 2006. About 10 years later, we first saw this in practice, and you can see here a very nice match between the observation and the actual theory. Well, then what about neutron stars? Is this also a scattering problem? Yes, it is also a scattering problem. You can think you start with two neutron stars, we give them some linear momentum, and you end up at the end of the day with a black hole plus gravitational waves producing this process. Now, when you go through the different stages of this process, there are two steps which are very important. At the merger, you don't produce a black hole in general, you produce what is called a hypermassive neutron star, or HMNS. This is an object that in principle should not exist in nature. Actually, you can't produce this object through quasi-stationary transformation. You can produce it dynamically, and this object is unstable. And so we want to find a new state, and this is the state of a black hole. So this object collapses to a black hole, and you produce then a black hole plus torus. We call torus whatever is not inside a black hole, whatever is outside and is orbiting unstable orbits. But these orbits become unstable because the system is losing angular momentum. And so even the torus then is accreted or is lost to infinity. And so at the end of the day, you end up with black hole plus gravitation. So these two stages don't exist in the case of black holes, and this is where all the complications are. But also all the interesting physics and astrophysics comes about. If we understand this part over here, the hypermassive neutron star, I will show that we have a very good tool to understand what is a neutron state. If we understand what happens when a black hole is formed, then maybe we understand what produces short primary bursts. We know that they exist. Now we know also they are associated with a merger of neutron stars. But how do we produce a jet, an ultra-relativistic jet at Lorentz factors of 100 or more when you just collide two objects? Okay, this is still pretty much a mystery. And then another important advantage of studying these objects is that they undergo nucleosynthesis. Just imagine you are meshing enormous nucleons, 3056 nucleons, at almost the speed of light, and as a result, some of this mass has so much kinetic energy that is gravitationally unbound. It will not fall into a black hole, it will just go and disappear at large distances. And this is very precious matter because it's already neutron rich, and so can undergo what is called arc process nucleosynthesis, rapid capture neutron capture process nucleosynthesis. And if you think about this, this is where we think gold is produced in nature. So if you have a piece of gold with you today, that piece of gold was not produced on Earth, it was found on Earth. But certainly was not produced on Earth, was not produced in stars, because stars cannot produce gold. So somewhere that gold must have been produced, and this cannot be on our planet. But calculations show that neutron stars are perfect to do this. Okay? So it's quite clear that neutron stars can produce gold. It's not clear they can produce points, but they can certainly produce. Now, how do you solve this problem? This very simple problem: binary neutron stars, binary black hole. Well, you have to solve the Einstein's equations. And not only that, you need also some other equations which tell you about the conservation of the right-hand side of these equations over here. So you need conservation of energy and momentum, conservation of rest mass, or whatever other charge you might have. And you also need an equation of state. And I have colored different equations with different colors because they are really different. And they require different techniques. I would say this a bit later. But this green box here, for us, is something that doesn't come from gravity, comes from microphysics, comes from fundamental interactions of atoms. And this is something that we have to take from experts, or maybe come up with some guess. Well, the energy momentum tensor here, you can think that is the linear combination of all the fields that are present in your system. So if you have, for instance, electromagnetic fields, then you will have that your T mu u over here will have also an electromagnetic constant. But then as soon as you start putting in electromagnetic fields, you need new conservation equations. And so you will need the Maxwell equation that tell you about how these fields actually evolve. If you have neutrinos, then you have to take care of how they are produced and they are radiated. So you need another part of this energy momentum tensor, which is associated with the flux of neutrinos. So Every time you want to make your description a bit more realistic, there are new equations that get solved, and the system becomes more complex. So I mentioned that we have to solve all of these equations, and you have to do this in 3D without symmetries, because intrinsically binary system doesn't have any symmetry. Now let me just spend a few words on the numerics. I will need a whole course to explain the numerics. But the basic and bottom line is that these equations are very different from these equations. These equations normally involve fields, which are gravitational fields, so the metric, the eccentric curvature, the gauges, and these are smooth fields. Okay? So you can use techniques which are well suited for solving partial differential equations with smooth functions. These other equations, the blue equations, matter equations, they are intrinsically involving things that will have discontinuities, because as you can imagine, when you smash two neutron stars, you are going to produce large shocks, large discontinuities. And so you need techniques that are studied and developed in order to follow exactly this dynamic. If you use the same techniques that you would use for solving the Einstein's equation, you would have failed to very imprecise descriptions. So in general, what we do is we use finite differences with second order spatial derivatives. For the Einstein's equation, we use finite volume, high resolution shock capturing methods with first order spatial derivatives to solve the algorithm. This is all I will say, but I'm ready to discuss details for anyone who is interested. This is really a different art that needs to be developed. And you don't develop this overnight. It takes years to build these codes. Luckily, many of these codes are now publicly available. So you can take these codes and do a simulation like this. So this is a simulation done with the code we have developed with a student, which involves a binary system of Newton stars. You can download this code, it's called PTHC. And I'm using a realistic equation of state, and these are an equal mass system of 1.35 solar masses. So this is not too far from reality. We start with irrotational bodies. These stars are not rotating. Then they evolve for a number of orbits. I'm showing you the density here. Then they get distorted, tidally distorted. This is a very important aspect. They become like polys instead of spheres. And then they rub very violently against each other. They produce this is the hypermassive neutron star I was mentioning. This is a peanut that is emitting a lot of gravitational waves and is losing angular momentum. And so it's becoming more compact and losing even more angular momentum because it's spinning faster. And then one point is so compact that you produce an apparent horizon. And so this is what we call a black hole clusters. Right? Now, this looks like computer graphics. It is not. It is really the solution of those equations that I was showing you before. So if you have to remember something out of what happens when two neutrons stars merge, this is the basic picture. You have a merger, you produce an hypermassive neutron star, and then you produce a black hole cluster.
Is the colors of the mass?
Yes, the best mass density. Yes. And,
Colors that we have.
yes, I haven't shown you. So you can think that the purple here is 10 to the 9 grams per cubic centimeter. And the blue is 10 to the 8, I think. So it's still very high density and high temperature. And the time scale is very short, okay? You may produce a black hole within 10 milliseconds or maybe up to a second. And this is important actually for what I will say later. So if this is the basic picture, what are the shades, the different flavors? Well, the total mass of the system obviously is important. Okay? Imagine that you start with a system which has a different mass, then the dynamics will be slightly different. And to explain this, I have come up with this funny diagram where I have time on the horizontal axis, and it's segment of time, so you go millions of years. And on the vertical axis, I have the mass of the system normalized to the maximum mass that a neutron star can support. It might rotate.
The neutron stars we start with, they have strong magnetic fields.
Well, no, really, they had strong magnetic when they were formed, but these objects are emerging millions or tens of millions after they were formed. So most likely their magnetic field has decayed. And so one expects very small magnetic field, 10 to the 10, which brings in an important question. How do you produce strong magnetic fields if you start with small magnetic fields, 10 to the 10? We know that in order to produce a jet, you need 10 to the 16, 10 to the 17 gas. How do you do this efficiently? So that's an important question we will have an answer to. Anyway, the system spent millions of years orbiting around each other, then produces another massive neutron star, and produces a black hole with a torus, and then eventually produces an isolated. So an isolated. Now imagine that you go up and you have a larger mass, then you simply wipe out this space. You immediately produce a black hole. Okay. Vice versa, we call this the front hole. Vice versa, if you have very low mass stars, say 1 solar mass, then maybe you will produce something which is uniformly rotating. Then maybe you end up with something which is not even rotating. A perfectly non-rotating star. This is something that you can in principle do. If the maximum mass is large enough, you can do this. And there is an interesting problem that you can study, that is the threshold mass, that is the mass at which these two cartoons are distinguished, that is the mass at which you dynamically produce a black hole. So again, something where Professor Davis has studied provided important picture. So that's how mass plays a role in this picture. Mass asymmetries are also important. Okay, the animation I've shown you, the two stars have the same mass. What happens if they do not have the same? And we know from observation that binary systems do not have the same mass. They have almost the same mass. The mass asymmetry is not large, but it's there. So again, you can use this code to tell you what happens in this case. So I'm showing you the evolution of a binary where there is a mass asymmetry of 20%, that's 0.8. So there is more massive star and a less massive star. Which one is the more massive star? Left or right? Right. Okay, this is funny. In astrophysics, the bigger the mass, the larger the radius. But for compact orbit, it's the other way around. So this is the heavy guy. Okay, it's smaller but heavier. So keep an eye on the small guy, because it's the small guy that really sets what's going on. And what it does is just strips matter from the lower mass. By doing this, it creates a lot of matter and then collapses very rapidly to a black hole. But also breaks up the other star, producing a very large disk. A lot of the matter is lost. Most of the a lot of dynamical ejected mass is produced. And so you lose a lot of mass, you produce, which then is going to produce gold, if you want, and you produce a very large torus, which is important. If you want to produce a gamma ray burst, you need a big torus, because essentially that's where all the energy is stored for the gamma rays. What are the other aspects? Equation of state is very important, as I will explain. Magnetic fields, no need to mention them. If you want to see something electromagnetically, you need magnetic fields. Radiative losses are also very important. Neutrinos, what is the role they have is they produce, they extract energy and angular momentum, so they can change the balance of the post-merger remnant, but also they can change how the nucleosynthesis is taking place, because these neutrinos will irradiate all the matter that has been ejected, so they will play a role also in that sense. Okay, now let me concentrate on this concept of gravitational wave spectroscopy. This is something again where a lot of people have contributed, and to understand this concept, let's take a gravitational wave signal. This is a typical gravitational wave signal from a binary neutron star. Let's see the fundamental pieces of it. There is one part which is the chirp signal. You can see that this is before the merger, and the amplitude is growing and the frequency is growing. This is the only thing we have seen in practice. Then there is going to be a transient where the two stars tend to find an equilibrium, which lasts a few milliseconds. And then there is this hypermassive neutron star stage where you produce gravitational waves, you can see very clearly that the frequency of the gas gravitational wave is much higher than the frequency at this during the spiral. That's why we don't see them, because our detectors are not sensitive to this high frequency. And then at one point, you just produce a black hole, and there's going to be a wind down and that side. If you compare this with a binary black hole, this is a binary black hole. Okay, I use the same color. So you can see binary black hole has red and blue. So it's missing all of this part on the post-merger. Black holes in comparison are trivial. Just they merge dynamically, produce a new black hole, voila, finished. So what we want to do is learn how to get information from this part over here. And this is what you can do. You can do a lot of simulations with different masses, different equation of state. This is an old simulation. And this set of simulation has taken 1 year of supercomputing time. And I can explain all you need to know in 1 minute. On top, you have soft equation of state. At the bottom, you have stiff equation of state. Low mass is on the left, high mass is on the right. Well, so the first thing you can see is that soft equation of state give you a remnant whose amplitude, gravitational wave amplitude, is much smaller than during the inspiral. Okay, so the amplitude here is much smaller. Look at here, extremely small. Vice versa, if you have a stiff equation of state, the opposite is true. The post-merger signal is comparable of that of the inspired. That's because you have the matter stiff equation of state means matter that you cannot really compress a lot. Okay, so you cannot really make it to a small object. It's a big object, big, large quadrupole moment, so it's losing a lot of angular momentum and producing a lot of gravitational radiation. You can see that this is, it's almost a continuum between soft and stiff. What else can you see? Well, the frequency of soft equation of state is higher than the frequency of stiff equations. This is clear. Here is just a blurred red. Here you can see some white between the blue. That's because a very soft equation of state means the object is very compact, is vibrating very, very high frequency. Well, another thing you can see is that this object, which is the most massive, most stiff equation of state, produces a black hole over this time scale. And that's because this object has lost so much angular momentum because it's so efficient radiator. By contrast, this object will certainly didn't collapse over the time scale we saw, and this may take maybe half a second before it collapses. So I don't know how long it took, but essentially that's all there is to read in this plot. And of course, the fact that you can see it in 1 minute is just because now you have a global picture that allows you to see the different details. Okay, when you do just one simulation, it's hard to understand how everything falls in place. Now, yes.
Why in the short scales the range is much similar to the center and the blue ones have larger range?
Yeah, so that's what I was saying. In a stiff equation of state, imagine the peanut that I was showing in the movie is very, very small. Because it's in the soft equation of state, the peanut is very compact, very compressed. And so it's not very good in producing gravitational waves. To produce gravitational waves, you want big separation, big quadrupole modes. That's why in the spiral, when the stars are far separated, you have such an advantage. Now, let's suppose we take a Fourier transform of this. That's what we get. Okay, interesting. Well, if you have studied astronomy, you must have studied astronomy in this building. These are lines. Okay, so you can think that these are spectra, and these are lines in a spectrum. And so, as in astronomy, you know how to understand what is the composition of a star by looking at the spectrum of the emitted radiation. Here, we can learn about the equation of state by just looking at where these peaks are. Okay? And this is where a lot of work Joseph Lula's group have done to learn how to correlate the position of these peaks with the properties of the equation of state. So that's why it's called gravitational wave spectroscopy, because you can use a spectrum to do spectrum with gravitational waves signals to do spectroscopy. If you are not convinced, let me show you a very simple example. So this is a stiff equational state over a given time scale. This is the time domain signal. This is the Fourier transform. The solid line refers just to the t larger than 0 signal. So you have to imagine that the signal actually goes back in frequency in this way, very low frequency of a lot of power. And what else? You can see that there are 3 peaks. We call F1, F2, F3. Other people call it in a different way, but concentrate on the largest one. Okay? It is clear that the largest one has to come from a time where the emission is almost constant in frequency. And in fact, you can show that these are the 2 peaks, F1 and F3, disappear if you start doing your Fourier transform from, say, 5 milliseconds onwards. So F1 and F3 are produced right after the merger. There is a nice toy mechanical model that explains this. Now, let's suppose you take another waveform for the soft equation. So this is red. The spiral is different. The post-merger is completely different. And yet, if you look at the post-merger spectrum, you still find that there is an F2, an F1, and an F3.
This does assume that there is then something of the time series, otherwise we impose frequencies in perspective, right?
Yeah, of course. And you know, so from the numerical point of view, this is easy to do because our time step is much smaller than this frequency, and these detectors have this frequency principle if they work at those frequencies.
Luciano, we have a question from Zoom.
Yes.
Go ahead.
And this Fourier transform is specifically after during the phase of like the hypermassive neutron star where you have the attenuation, not before the merger, not the chip phase, right?
Yeah, so I have used, let me go here. The solid line is just t larger than 0. The dotted line is from minus, I don't know, 20 milliseconds up to 0. So if you want, the dotted line is the spiral only, and the solid line is the post-merger.
Thank you.
So, okay, a question just to see if there is a frequency here, which is the frequency at merger. So you can calculate when is the merger. How do you calculate this? You look at the gravitational wave amplitude. You look where it is the maximum effect. At this time, they merge. It's not when they touch, because it's very hard to define when they touch, but you can define it mathematically in this form. Now, this is for a stiff equational state. If you look at the soft equational state, it moves to higher frequency. Everything actually moves to higher frequency. And this is what I was explaining. Soft equational state move the spectrum to higher frequency. So by just, looking at this basic behavior, stiffness tends to lower the frequency, softness to higher frequency. You can already see how there is a correlation. And I will not go more in detail into this. There are a lot of universal relations, but also Judas and myself have derived for how to go from the position of the maximum amplitude over to the properties of the equation. Okay. I will switch topic and I will go now about these 2 detections that has been done. So this is GW17 over 17. You probably have seen this. This is the frequency evolution. This is a spectrogram. At one point, we don't see it anymore. That's probably because it's become too high frequency for the detector. And then at 1.7 seconds later, we see this signal over here in electromagnetic region, gamma rays. So this was a fantastic episode. We thought we would see many more of these. Unfortunately, we haven't. But this single event has already given us a very important piece of information. That's the maximum mass of neutron stars. So out of this number, 2.74, you can set an upper limit on the maximum mass. It's hard to believe you can do this, but let me show how you do it. So if you study, being in Thessaloniki, you will know all this very well, right? So I don't need to to teach you about the TOD equation. You can solve the TOD equation and you can obtain a sequence of equilibria from self-gravitating, non-rotating stars, which has a maximum we call this MTOB. To the right MTOB, you are unstable. To the left, you are stable. And this diagram is a funny diagram, doesn't have any number. That's because every equation state will change this curve. We will move it either up or down, left or right, depending on its difference. Okay, now there are more solutions in this space, and these are the solutions which are uniformly rotating. You take the non-rotating stuff, you start spinning them, and then at one point you reach the limit there where if you spin them a little bit more, you break. Okay, then it's called mass shedding or Keplerian limit. And also this limit has a maximum, which we call the maximum mass for rotating configuration. You can show that there is a stability line, which is given by all the constant angular momentum sequences, and is the turning point of that. So you can think that anything to the right of this line is unstable and produces a black hole. Everything is instead stable. There are more solutions, but let me first now make a consideration. We don't know what is MTOB, we don't know what is Mmax, but we know what is the ratio between them. And this ratio is about 20–25%, quite independently of the equation of state. So if you know Mmax, maybe you know MTOB. There are more solutions. These are differentially rotating stars, and these are over here. Okay, they can be much larger in mass. They can have smaller central density. That's because they are differentially rotating. And again, you can show there is a stability line, so that to the left of this line you are stable, to the right you are unstable. Okay, now that was just a recap. When GW17 or 17 happened, it produced a differentially rotating star, hypermassive neutron star. That means, in terms of equilibria, it must have been somewhere here across. We also know that there was a gamma ray burst observed, and that means that a black hole must have been produced, which means that this guy must have crossed the line. Somewhere it must have crossed the line because it has produced a black hole. And you have essentially two options. One is option 2, and the other one is option 1. Option 2 is the hypermassive neutron star collapses to a black hole while still differentially rotating. In the movie I've shown you, that's what happened. The hypermassive neutron star was still differentially rotating when it collapsed to a black hole. In route 1, instead, you enter into this green region, most of it becomes uniformly rotating, and then you cross the equilibrium. We don't think that 2 is right. The reason is that we saw a very bright kilonova. And to produce a bright kilonova, you need to lose a lot of matter. And to lose a lot of matter, you have to survive for a long time. In fact, we have estimated you survive about 0.9 seconds. So what we believe is that it has followed route number 1. And so the collapse must have happened very close to Mmax. And now you have a tool to set an estimate on Mmax. Okay, so let me stress again the logic here. You consider track number 1. You use the mass measured gravitational mass measured in GW17. You take away the rest mass that has been lost, and you know this from the kilonova, and then you can set a new relation, a new upper limit for the maximum mass. Of course, there is some errors and uncertainty in this, because all of these quantities are measured to the position. And this is it. The Parser timing tells us that it has to be larger than 2.1, 0.01. And this estimate tells you that it has to be smaller than 2.3. Okay? I know this sounds like a contorted logical path, but if you don't believe me, don't worry. Because around about the same time when we came up with this result, there were 3 other groups which had essentially got the same result, following different routes. So maybe I'm completely wrong, but the answer is still right. So we do believe that 2.3 is the maximum mass you can have in a neutron star.
Is the error pass at least 1 sigma or 90%?
These are two sigma. Yeah. So we were quite happy that there was this agreement about different groups about the maximum mass, and then this guy came out, 1908-14. Why? Well, this really broke all of our hopes, of our uncertainties, because this system has the primary, the big guy, has 20-something solar masses. So this is obviously a black hole and the neutron stuff. But the second one, well, it's either the smallest black hole or the heaviest neutron star. And how do you find out? Well, of course, if it is a neutron star, then all our saying is wrong. Okay, let's forget it. It's just not right. Well, the problem with this detection is that we didn't see any counterpart. And so all of this consideration about how we must have collapsed to a black hole, I can estimate what is a reflected mass, cannot be used. So how do you resolve this tension? Well, what you do as a physicist, you say, okay, let's explore this possibility and let's see whether or not it is in contrast with other things. If it is not in contrast, then maybe it's right. So we have carried out an analysis where we have considered the possibility that actually there are stars that are larger than 2.5 solar masses. And then we have built a model which then tells us if there is a distribution that has stars with such large masses, what are the consequences? You can write this into a multi-dimensional problem with lots of parameters. The parameters are all the things you don't know precisely. So these are coefficients that you put, just to give you an idea, this would be how much mass is in the disk, how much mass in the disk is lost through winds, how much mass is ejected in kilonova, and so on. And then you try to compare this with all the other constraints that you know. At the end of the day, you have a 10-parameter space that you have to minimize. And we did this using what is called a genetic algorithm. This is a very interesting algorithm, works like genetics. You make a variation, a mutation in your set of coefficients. If the mutation leads to an improvement, it's a good mutation, so you keep it. If it provides you a worse chi-square, then you throw it away because there's a bad mutation. It's very easy to implement and code, much more than an MCMC. So the first thing we did was testing the code and see if things worked out. And so we considered the hypothesis, the prior, that the maximum mass is really 2.3. And then we got a posterior, so this is the posterior distribution, blue one, using this model. And it fits very nicely with the previous estimate that we had done with this rough estimate I was giving you. We also checked if this population provided gravitational waves in the expected range. And this is shown over here. So this is what you would expect from numerical relativity simulations. This is the distribution of the emitted gravitational waves. So this is the amount of mass lost through gravitational waves. So you can see you can lose almost 0.2 solar masses. And this distribution is actually the sum of two distributions, the mass lost during the spiral plus the mass lost after the merger. And this is amazing how after the merger, you lose 3-4 times the mass you lost through all of the spiral. The spiral can last millions of years. The post-merger can last 1 second, but you lose more after the merger than before. You can also check how much mass would be lost in ejecta. And the green shaded line region tells you the constraints from GW17 and 17. And again, the distribution fits pretty well with the expectation. So 2.3 doesn't break anything that we know. Then you can try and do the same exercise for 2.4, 2.5, and you find out that you tend to overproduce gravitational waves and you tend to underproduce ejected mass. The reason is pretty simple. If you allow your distribution of masses to have big masses, these are very efficient emitter of gravitational waves, so they overproduce gravitational waves. but they also tend to collapse very rapidly, and so they underproduce ejecta. So, this doesn't prove anything, but at least shows that if you go along this assumption of having high masses, then you can't explain numerical activity, you can't explain phenomena. Unless you say GW17 or 17 was a very special case. So how do you solve this tension? Well, in my view, you solve this tension by saying M, its secondary was already a black. At the merger was a black hole. Maybe it was a neutron star before, but at the merger was a black hole. And this also explains why there was no counterpart, because you don't expect a counterpart from two black holes. Of course, this doesn't prove anything, but I think it strengthens our impression that 2.3 is really the. Let me go now to a very different topic, which is space transitions. I work in Frankfurt, and Frankfurt, there are a lot of people who work in QCD. So they like to think that nature can be written in a phase diagram. Okay? So this is a phase diagram. You have temperature on one axis, you have chemical baryon potential on the other axis. And so low chemical baryon potential is the universe, in particular over here you have the universe. Neutron stars are on the opposite axis. They are very cold, but also very dense. This is lattice QCD, this is low energy at the ion collision. Neutron star mergers, they probe the same density, but at much higher temperatures, 70 to 80 MeVs. So you explore a region that is not covered by anything else. So that's why they are so precious. And they happen to be in a region where maybe, so this line here is the expected first order phase transition between hadrons on the left and quarks on the right. So maybe neutron stars can probe what happens when you cross this line. And that's what we've done. We have done simulations where we have considered the possibility of an equational state to either be fully hadronic, this is the black curve, or to have an unstable branch where quark matter is present. And we carry out two different simulations, with and without quarks, and see what are the consequences. Okay, this is shown in this movie, which is a very complicated movie. So I will need, just to explain what's shown, take some time. All right, so you have temperature with this color code, you have quark fraction with this other color code. Here you have XY plane, here you have zeta X plane. So this is a polar cut, a meridional cut if you want, and this is just the equatorial plane. And the green lines, these are contours of equal density, okay? So this is in saturation values 1.5 and 6.
These are the two objects.
These are the two objects.
Right.
These are the two objects in the two planes. Then they merge, and you can see already here that there where it's hot, you start using quarks. But these quarks are, they can be produced and then disappear depending on the change of temperature, because you are going in different parts of the phase diagram. And then at one point, you are getting so high temperatures and density at the center that the whole core of the supermassive neutron star, undergoes a phase transition. And that's its end. At that point, the equational state becomes very, very soft, and the star can no longer sustain itself. Maybe this is best seen over here in these snapshots. You see that there where it's hot is also, you have a higher quark fraction. See that here again. And then at the center, you have the quark fraction goes to 1. That means this is a quark core. And at this point, all of this guy has a much lower pressure, and the thing just collapses. You can see this also in terms of phase diagram. This is an even more complicated plot. You can think of looking at the place in the star with the highest density and the highest temperature, and follow the evolution in the phase diagram. And you follow the evolution by looking at the time at different times, and the color bar stands with the time. Okay, so let's have a look first at the temperature. This is the temperature at the beginning. It's dark brown, so over here 6 milliseconds, 8 milliseconds after the merger, you are in this region of high temperature but low density, comparatively low density. But then later on, you start moving to higher and higher density, and then you cross the phase transition. And once you cross the phase transition, you are doomed. Of course, you're not going to see the phase diagram. What you will see is the actual gravitational wave, and the gravitational waves are very, very clear. So this is the amplitude, this is the frequency, and this is the phase difference. This is the difference in phase between the red and the black. So during the inspiral, the phase difference is 0. In fact, you can see black and red are on top of each other. That's because there are no quarks yet. It starts as still too cold to produce quarks. But then later on, they emerge, you start producing quarks, not a lot, a little bit, but this is sufficient to produce a phase difference. And then, as soon as the phase transition is complete, you produce a collapse turbulence. Okay? So this is a way, in principle, to establish how a phase transition takes place. It's a signature of it. You would look at the inspiral and say, oh, this is clearly an hadronic equation of state because it matches perfectly my prediction, but then your prediction tells you should collapse here, and then you collapse earlier. So this will be a very strong indication that there is a phase transition. It's not the most convincing one. I'll tell you why, but it's a signature. We have then started considering, but also Professor Julia started looking at different ways in which you can find signatures. And then we created a classification of possibilities. And these are shown all in a cartoon. So this is the standard evolution of the gravitational wave frequency. So it starts growing, just like here, it grows. And there is the merger, then you have the F2 frequency, which remains for a very long time. This is what I've shown you. You have a phase transition which gradually takes place, and then when it is complete, you produce a collapse. We call this phase transition triggered collapse. This is something that Professor Sedrudas, I think you have worked on with Bob and yeah. So Professor Sedrudas is suggesting instead that at the merger you produce a stable object, which is a hybrid object, which has a core made of quarks, and so vibrates at a higher frequency. We call this prompt phase transition. And another possibility is you have a delayed phase transition, which is similar to this blue one, but instead of producing a black hole, you produce an object now that is stable. And we think this is the most interesting of all the cases. Okay? These are some, examples that it's not just cartoons. You can calculate this consistently. This is an example of a delayed phase transition. You start here and then you translate over to another object which is more compact, as a stable quark core, and it is emitting in a higher frequency. And this is, in my view, the most important or clear signature, because in the case of an hadronic equation of state, you have a single F2 mode, F2 peak. In the case of this phase transition, delayed phase transition, you would have two, okay? One, which is the first one at low frequency, when the star was still fully hadronic, and the other one later on when the star has a quark. So if we see two strong F2 peaks, I think there is just no other way to explain it. But this also shows you.
Have you confused the second peak with something else?
No, really. I think, this guy is what you would expect knowing the inspiral. But the inspiral and this guy have to be the same, okay, from the same state. And if you start seeing something else at a higher frequency, you can't explain. That's a phase transition must have. This also shows you that a theorist is an incurable optimist. We haven't seen any of these signals, and probably we're not going to see for the next 10, 15 years, but I'm telling you how important they will be. Okay, I don't know much. So the next thing is talking about a sound speed in neutron stars. So the equation of state is still unclear. And for someone who is not a nuclear physicist like myself, the equation of state is essentially a prescription between pressure and energy density. So it's a curve in this diagram over here. Neutron stars at most go at these energies over here. Okay, so in principle, the equation of state that we can test goes into this pink region over here. We can also test at much lower density and much lower pressures. We can do this with experiments in the lab. We can have nuclear theory, which helps us, because there we think we understand things. We also think we understand QCD, or perturbative QCD allows us to give us a relation between P and E in these regions over here. Of course, we cannot test this, but we believe QCD is correct. And in the early universe, this region was certainly popular. So for someone like me, I can think that what I need is a curve that just matches these two constraints. I don't know what the Lagrangian. I hope to be forgiven if I don't consider this. But to me, this is just a curve I have to match between these two extremes. But then I can start asking myself questions, statistical questions, like, okay, if I build an equation of state, can I tell if the sound speed inside the star is always subconformal, that is always less than 1 square meter, or no, 1/3? So this is the blue region here. Does the sound speed behave like this? Or is subconformal, but then is not monotonic? Or is super conformal? It goes above 1/3 and then comes down. It has to go to 1/3 at the end, because this is what PQCD says. So what we do is we just say we don't know what is the right answer. We just throw a lot of these lines, and we do this by parameterizing the sound speed. So we write an agnostic guesswork of what the sound speed can look like. And then from each of these guesses, we build an equation of state. And from each of these equation of state, we get a mass radius curve. And we compare with what we know from observations, the radii and the maximum mass. And we do this 15 million times. So we build 15 million equations of state. 90% of them are bad, and we throw them away. But 10% remains, and these are now interesting, statistically interesting, because we can do some statistical considerations. So, for instance, you can convince yourself that statistically you expect that the sound speed goes above the conformal limit. This is clearly shown over here. There is a maximum, and somewhere inside the star, the sound speed must be larger than 1 square of speed. And the possibility instead is always subconformal, so it's given by this orange line, and this is extremely small, less than 0.03% of the whole sample satisfies this constraint. So this doesn't tell you a straight answer, but tells you that statistically you expect the sound speed to go above 1/3, sound speed squared. And I think this is already important because this was a question that people didn't know. You can use this same distribution in terms of equations of state, and this is the distribution in terms of equation of state. The black curves is the 95% confidence limit, and the blue tells you, the shading in blue tells you the different probability. Okay, so we think these are where all of those curves in principle can make. What else? You can also do then the same for mass and radii, and this is very interesting now because this tells you that, okay, in principle you can have 3 solar masses, but in general you tend to have not so high probability of having this event. And you can also see that now you have the possibility, because you have a distribution, to say given a cut at 1.4 solar masses, this is given by the red curve, what is the average or the median radius? And for instance, you see that the median radius of 1.4 is 12.4 kilometers. If you are 2 solar masses, it is smaller, 12.1. This line over here, I like it in particular because this is using actually a result by Professor Segulas about the maximum, the minimum radius that you have to have in order not to collapse. This is by doing simulation and checking what is the maximum mass of which you produce, the minimum mass of which you produce a black hole immediately. And you can see that, so this line comes from completely different considerations and yet matches very well what you would expect. So in practice, this means that I really don't believe equations of state that are smaller than 10 kilometers to be realistic. Another, maybe the most important result of all of this analysis is this one here. So this is the chip mass as a function of the tidal deformability. Tidal deformability is a fingerprint of the equation of state. And we built out of these equations of state, we built the chip mass and the distribution of the chip mass, and you see that it is very nicely upper bounded by this 2 dash line, upper bounded, lower bounded by this 2 dash lines. Now, the chip mass is the best measured quantity in an inspirer. It's measured to 1% precision. In the case of GW17, this was measured to this number. This means that in principle, you can cut this with a line, and you have a lower limit and an upper limit. And interestingly, this upper limit matches what LIGO has also deduced. Okay, it doesn't surprise you. We use that limit, but now we have a lower limit. And because this is all analytic, as soon as there is a new measurement of the chip mass, you can immediately set some measurement of what is the tidal deformability. Okay. Now, what is a bit frustrating about this representation over here is that it tells you that somewhere the sound speed becomes larger than square root of 1 over square root of 3, but it doesn't tell you where. Okay, where does the sound speed become large inside the star? And there was a very frustrating question we couldn't find an answer to. So went wrong direction. And so what we did, we thought about this problem. How does the sound speed vary in a star? Is the maximum sound speed at the center of the star? Does the maximum value obtain a constant value or not? So these are very simple questions. Okay? Now, if you asked me before the study, where does the sound speed reach its maximum, I would have said at the center, of course. That's where the density is higher, I would expect there where the sound speed is the largest. And that has turned out to be not quite right, or at least not fully right. The problem of this problem, is that every equation of state will give you different radius and different theory mass. So how do you compare these millions of equations of state and billions of stellar models? But if you think a little bit about this, well, you can drive all of this space of solutions in a unit cube. But instead of using the radius r, you use the normalized radius between 0 and 1. And instead of using the mass between 0 and 2d, you use the normalized mass between that. Then you have a cube, which is between 0 and 1. So you have all the space of solutions into a unit cube. It's a bit like a conformal diagram. You have everything into a finite space. And that's what we've done. And this is a bit complicated picture to look at. So let's do it slowly. This is the sound speed in the vertical axis between 0 and f1a. That's the maximum you will really reach. This is the normalized radius. So 0 is the center and 1 is the surface. So the surface, the sound speed goes to 0. That's what you expect. And this is the mass over empty of it. So this is light stars, this is heavy stars in this way. Okay, so you can calculate what is the maximum, and the maximum is indeed at the center. But then as you start increasing the mass, the maximum goes away, and actually the maximum sound speed is in the other lanes, is in the mountain, like 0.6, 0.5. And if you look at the maximum sound speed, it actually reaches almost a constant value, so a very massive stars. This is, you can also see that the sound speed at the center, which is over here, actually goes down as the mass increases. So as you make a star more and more massive, the sound speed is maximum is not at the center, and the sound speed at the center actually increases. You can also see this from these sections. So these are sections. So these are I'm taking sections along this direction, like MMTOB. You can see how for light stars you have this behavior, and if you have heavy stars, the maximum is at 0.6 or so. So you can think and associate this with stiffness. Okay? If the maximum is associated with the maximum stiffness, then the maximum stiffness in a low mass star is at the center, and in a high mass star is not at the center, is in the mantle. So these were two papers that we published. They were both letters, and they were both coming next to each other in the same volume. And the journal said we should write a press release on this, but you have to write a press release in a way which is comprehensible for everybody about this result. So a shower was very important because I was having a shower, and then I had this idea. The idea is you want to translate light stars have a stiff core and a soft mantle. Heavy stars have a soft core and a stiff mantle. Voila. I thought of pralines. Okay. So you can think that light stars are like those chocolates that have a nut at the center. Okay? And instead, heavy stars are those chocolates that have a soft center but have a hard shell. We made this press release. This was quite an impact because FSZ, the Frankfurt Allgemeine Zeitung, picked it up and defined this as the sweetest discovery of the year. The lesson to learn is that if you want people to read your science, use chocolate. Okay, I think that I'll come to my conclusions. I've shown you that if you look at the post-merger, there are peaks, and these peaks are quasi-universal. I've shown you how only two detections have already given us a very good idea about what to expect in terms of maximum mass, radii, and maximum mobility. A phase transition can leave a signature. You just don't know exactly what is the right signature. The sound speed cannot be subconformal everywhere, but must be somewhere superconformal. And where it is superconformal will depend on the mass. The sound speed is monotonic in light stars, so everything is much more at the center, and non-monotonic in light stars. Thank you for your attention.
Thank you very much, Luciano, for this excellent talk. So we have time for questions, both from the audience here and from the audience to the Zoom call.
I've been talking for an hour. I hope we will answer.
Yes, go ahead.
This is about finding the right model for the. So then you said about how the code will change the model for short bits, and we find it's better to do a prediction or not. Now let us, how do we know that we're not stuck in a local minimum? It's not wrong to be stuck on the model that's not perfect, but it's better than
Okay, so this is a typical question you ask when you are doing a minimization problem. Okay, you know that the problem has many parameters, and so you can think many parameters on many dimensions, and you walk in this high-dimensional space trying to find the minimum. And you find a minimum, and you ask yourself, is there another minimum nearby? And you normally answer this question by looking around you and then seeing if there is another minimum. If there is another minimum, then you say, okay, that minimum is not really the best minimum. I prefer this. So you have to iteratively do this. But yeah, this is a very common problem in this mini-related activities.
Professor Rezzolla?
Yeah, I think the question is in the beginning when you saw these animations, you saw that you described these simulations, so comparing the experiment. I think this intermediate, looking for this resonance, I don't know how to call it, this hyper massive Neutron star. Yes. What is the matter of this?
Well, essentially, it's the mass of the system. Okay, so in the case of GW17 is 2.7 minus something. So mass is conserved. And if you think about rest mass, so not relative mass, but the rest mass, it's essentially the same rest mass of the two stars at the beginning, minus all the one they lost. Okay, so it's roughly 2.7 in that case. So if you want to have a ballpark reference, 1% of the mass is lost by this.
Professor Lapp?
In your code, you mentioned that you have a radiation, you have radiation calculated. So you calculate also the magnetic radiation in this code, or what did you do with the electromagnetic radiation? If it's there, how did you explain the gamma ray production of in this environment?
So we do calculate electromagnetic radiation, and we do this in a most obvious way, but also maybe not perfectly correct. And that is, we calculate the Poynting flux. So we take a surface, large surface, and we calculate what is the Poynting flux at this surface. If you were in vacuum, this would tell you the radiated electromagnetic energy. But we are not quite in vacuum, and that is why maybe this is not a very good measurement. But it's a rough measurement that tells you about how much electromagnetic power is radiated. And that also tells you where it is radiated. You find out that this power is radiated mostly in the polar region, so something that looks like a jet. So producing a collimated radiation is not a problem for our boats. We were able to do this already 10, 15 years ago. What is more difficult is to produce an ultra-relativistic jet. The matter that is ejected along this funnel is mildly relativistic. Gamma Lorentz factor of order 3, 4. So we do not have yet the ability to describe this. And the reason why we are not is because we're using magnetohydrodynamics. So we still have a plasma there, while most likely in this jet you have force-free conditions. They are essentially in vacuum, but with very strong magnetization. And this is a difficult regime to describe with MHD simulations. So we are improving, but the ballpark luminosity that we get is what you would expect: 10 to the 51, 10 to the 52 per second.
But we know that there is electromagnetic radiation coming down. But what about you have regime on the kitchen sheet? So when you use gamma ray, or is it?
No. So this is completely bolometric measurement. We have no idea what is the actual frequency we expect in this simulation.
So we have a question from Zoom.
Yep.
Can we go back to the diagram with that 3D diagram that shows the speed of sound in the relation to some other two parameters?
This one.
Yeah, this one. In this diagram, the speed of sound is like based on is this like a median from those previous models? How do you get this figure?
Yeah, so
the speed of sound.
It's the blue line is the median, and the other two lines are the 95% confidence level. If you want to have a more precise look, this is a figure which shows both the median. This is the red. This is the black lines are the 95%, and then the color code. The color code tells you the PDF more in detail.
Yeah, I wanted to ask, because I feel like the median here, or like the likelihood that you describe, is wouldn't it be very much biased by the way you generate these models? Because I feel like can you really do statistics in this sort of, this isn't experimental data, this is more like these fits that you generate, and then you do some sort of analysis of these models. But here, like, to say what something is more likely to happen is sort of strange. How did you justify that?
Okay. I'm not sure why you find it strange. I mean, imagine this is simulate is data you collect out of an experiment. Okay. If all you had it was the data between the left panel and the middle panel, then you would say, well, I can't really tell you much. What I can say is that the sound speed is larger at the center and is super conformal at the center. But if you look at the third panel, well, the behavior is very different. All of the confidence limits show you that the maximum is not at the center, no matter which confidence level you choose. Even the lower confidence level, the highest confidence level, tells you that the maximum is not at the center. So I think this is, a good way of saying, well, for very high mass, the sound speed maximum is not at the center, and actually at the center is below the conformal limit.
So it's a generic feature of all of these, or most of these? How?
I would say it's a generic feature of all of these. What I cannot say with confidence is whether at the center it is super or subconformal, because you see that there are some
Okay.
that are super conformal and some that are subconformal. So that is something we don't state. But the fact that the maximum moves away from the center and it does this in a systematic way, I think this is robust.
Professor
All right, thank you.
Yeah.
I just want to ask because we began the medical and also the sound. Both of them are multi-parametric amorphous, and I'm just thinking if the diagrams are modified in order to find what is best meaning, in order to get best result and find out what are the best values in order to see support the next code and also the issue about the of the sound.
So I'm not familiar with the Lagrange multiplier approach in these multi-parametric problems. The ones I am familiar with are the genetic algorithms and the Markov chain multipliers. But if you think Lagrange multipliers would do this job, then yes, why not?
Those would be something like lambda, then you can find even. There is lambda going to give you the best value, it's the best meaning.
Yeah, okay, yes. Yeah.
And the other thing that I would like to ask you is, so you consider the case, there is the interpretation of there is the gravitational coming. In that, maybe this is the gravitational actually calculation. So there's a frequency, so actually the sound of the gravitational wave.
Well, these are not sound waves. So anyway, you would have to map the gravitational wave signal into a sound. If you have a scenario like this, then it is very close to what is within our ear range, because our ear range goes between, I think, 200 hertz and 20 kilohertz. The highest frequency here are around 3 kilohertz, so we would definitely be able to hear it. And in fact, there are some examples of people who have translated its waveforms into sound. It's music, yes, it's the music of the universe.
Professor Bartolopoulos,
to understand lots of things of the conformal limit. The conformal limit that's stating the speed side.
It's very easy. At high density, you have a non-relativistic fluid. The ratio between pressure and energy density is 1/3. P equal 1/3 E. Sound speed is P dP over dE. and that's where you get number.
Another question?
So, can you go back to the slide where you showed the binary collapse with the electromagnetic counterparts? When you had this.
The
cartoon-
spectral.
No, the cartoon figure where you showed the two possible outcomes. No, way back. The 17.
Oh, okay,
The binary neutron stuff.
yes.
So my question is, I mean, this is a cartoon, I know, but can the path number one, how does it evolve after you enter the region of, uniform rotation?
Very good, Jacob. That's a very good question.
Yeah.
Now,
Because of, when you get to uniform rotation, then you are stable. In a sense.
exactly. And that's what we use.
Yeah.
Because in principle, it says you enter in the green region, then, well, how do you know where you have collapsed? You could have collapsed here, or maybe you have collapsed over here. We use the fact that once you are entered this region, that you are almost inefficient in rotational waves, to say that the red line must have been very close
Close
to
one.
Yeah. So that's how we resolve this problem. The time scale, the evolution here becomes days, if not years.
Mhm.
Okay, and we know it collapsed after 1.7 seconds, so it must have landed very close.
Because I guess you don't have that much mass available to, fall in and have that cause the collapse.
Yeah.
So,
Yeah.
I never understand if the design street is running to the density. How do you ensure that the star will
Okay, so all of these stars are stable because they are non-rotating stars and they are on the stable branch. So maybe I don't know if so. The question you're asking is why does it do this? Why heavy stars do not have this the maximum sound speed at the center? Is that your question?
Yes.
Okay, the rotation is a different question, but I'm almost. Okay, so when I looked at this, I also asked myself, why should an heavy star have the sound speed here and not at the center? And I've been puzzling about this question for a long time. And I think it's the way the star finds an equilibrium with very large masses. If you had a very large mass, then and the sound speed was here, this means that you have a large central pressure. Now, large central pressure means it's bad for gravity because large pressure gravitates. Pressure in general relativity gravitates. So if you think about the TOV equation, is E plus P. The pressure plays the same role as the energy density, as the density in Newtonian star. So you cannot have very high pressures at the center. And so what the star does is it tries to put the pressure away from the center by creating this very stiff region outside. And that's why the praline actually is a good example. So it's like as if the star is very rigid in the outer layers. And this rigidity allows it to have very large masses. If we didn't have this rigidity and the rigidity was at the center, it would collapse.
I have a related question
Okay.
about the speed of sound. The speed of sound plays a critical role in determining the frequency of the oscillation.
Mhm.
For example, the Richter frequency. And you know that the fundamental Richter frequency goes to zero in the maximum mass.
Mhm.
And I'm wondering if you look at for a possible correlation between the speed of sound becoming smaller at the center,
Mhm.
whereas at the same time, the fundamental Richter frequency also decreases.
We haven't looked into this, but I would expect
there
that
could be a correlation.